All right, so it might be best to just divide the page up into two sections here. Basically looking at two different types of autotransformers here. We got the step down and the step up autotransformer. You can see that they basically just draw a single winding here, right? It's just one coil, but they take the primary for the step down transformer, they take the primary across the entire coil, and they take the secondary only across a segment of the coil, and they still have the two dots, so we're treating it like a transformer, but it's just a single winding where we have the full coil as our primary and a segment of the coil as our secondary, and so that's how we get a step down transformer behavior. And so we can basically just start with the voltage ratios here. We know V2 over V1 is equal to N2 over, V2 over V1 is going to be equal to basically N2 over N1. But in this case, N1 is the number of turns total, right? So they're showing you that N is basically the total number of turns, and then this top segment has N1 turns, and this bottom segment has N2 turns. So we can write here that N, the total number of turns, is basically the sum of the turns above the tap and the number of turns below the tap, okay? So we could write that V2 over V1 is equal to N2 over N, which is the total number of turns. That's my primary number of turns. And so I can basically write that that's equal to N2 over N1 plus N2 for the autotransformer. And then, of course, my current is going to be the opposite. It's just going to be I2 over I1. It's going to give me N over N2, which is equal to N1 plus N2 over N2. Okay, so that's for the step down autotransformer. How about the step up autotransformer? Basically the same thing going on here with the turns. We can still see that the total number of turns N is on the secondary, and it's N1 plus N2. Again, they're showing you that N1 is here and N2 is here, and that total number of turns is now our secondary, right? The full winding was our primary in the step down case, and now the full winding is our secondary in the step up case, right? Which makes sense because we have less turns here than we do here, so that should give us a step up voltage characteristic. And so if we do the math here, we're basically going to write V2 over V1 is going to be equal to N, right? The number of turns on the secondary divided by N1, and that's going to basically give me N1 plus N2 over N1 for the voltage. Current, of course, is just going to be the opposite of that, so it's going to be N1 over N, which gives me N1 over N1 plus N2. Okay, so it's just that simple, and that's going to be the expressions that we get. Oh, sorry, I think I screwed this up. The number of turns N1 is actually irrelevant here. It's N2 that they're using for the primary. Sorry about that. So you can see that the primary is using N2. N1 is not relevant for this derivation. So it's going to be N over N2, which gives me the sum over N2. And then, yeah, sorry about that. I just went into autopilot for a second. So this is just going to be the opposite, which is N2 over N, which gives me N2 over N1 plus N2. Okay, so those are the equations for the autotransformers, okay? So if you see an autotransformer, don't freak out. Just note that you have to take these things into account. And like I said, we have to take KCL into account as well. So if you're looking at this, in the previous case, we didn't have to think about this, but now we have to take into account that I1 is going to branch off into I2 and then some other current here. We could call it IX if you want, but this current here is not going to be I1. It's going to be IX, some value that's I1 minus I2. Okay, so that's another thing to keep in mind. We're going to solve an autotransformer problem. I have one loaded up, and so that'll be the next video, and we'll see you guys for that example in the next one.